welcome back to Algebra 1. Today we're going to be doing lesson 14.1, so we're going to be starting a new unit today. This unit is all about quadratic equations and stuff, so we're going to get back into graphing a little bit, as well as formulating the equations, learning about the quadratic equations, and everything we've been doing so far has been building up to basically this unit. So today we're going to be learning about the first degree and quadratic equations, as well as we're going to be doing 14.2, graphing solutions of quadratic equations. So if we have the equation x minus 1 equals 0, this is what we call an equation of the first degree. And because it only has one root, x equals 1. Similarly, if we had x minus 5 equals 0, or realistically anything with one unknown, one known equaling something, equaling a single digit or equaling something that's attainable, something realistic, those would be considered first degrees, as the roots would come out to be the unknown equaling a rational number. Consequently, however, the product of any two linear equations, such as x minus 1 multiplied by x minus 5, all equaling 0, or alternately, after foiling, x squared minus 6x plus 5 equaling 0. This would be an equation of the second degree, as it would have two roots. Therefore, we can logically conclude that if an answer were to somehow have more than two roots, it would be of the third degree or fourth degree, and so on. Right now, you're only going to be focusing on any equations that have two roots, therefore only realistically second degree equations, or vice versa, a first degree equation with only one root. So, an equation which, when simplified, contains the square of the unknown number but no higher power, it is called an equation of the second degree, or a quadratic equation. Then we have our quadratic equation, which can be written in a formula form of y equals ax squared plus bx plus c. This is what we call our quadratic equation. In the equations examined up to this point, if there was one unknown number, there was but one value that unknown number, or one root. In order that we may more clearly see why we have two roots in these new equations, we shall study the graphs of certain types of quadratic equations and how the graphs give us a method of solution. So we're going to look at a couple and figure out how they would look and what they would do. Okay, so we're going to move on to 14.2, which is graphing solutions of a quadratic equation. Now, they're going to give you three examples here, but realistically, all three examples are basically the same example, but with a couple of numbers changed. And I'm going to show you what I mean by that, don't worry. But I'm going to show you how they build on each other and how they change and differ. Alright? So, to solve x squared minus 6x plus 5 equals 0 graphically, we must first draw the graph of that equation. To do this, we would actually let all of this equal y instead of 0. And this way, we then have our x and y that we're solving for. So the graph of y equals x squared minus 6x plus 5 represent all the corresponding real values of x and of x squared minus 6x plus 5. Among them will be the values of x that make x squared minus 6x plus 5 equal to 0. That is, the roots of the equation x squared minus 6x equals 5, or plus 5 equals 0. So when the coefficient of x squared is plus 1, as in this instance, it is convenient to take for the first value of x a number equal to half the coefficient of x with its sign changed. Next, values of x differing from this value by equal amounts may be taken. So this means that if this equation here has basically a 1 in it, then it's easiest to take this equation, or this part of the equation, and take half of that. So in this instance, we would take 3, as 3 is half of 6. And so we'd start there. So we'd make x equal 3, and we'd plug that into all of our equations. So we'd say 3 squared minus 6 times 3 plus 5 equals y. Now, first substituting x equals 3, we find that y would then equal -4 if we were to sit here and solve all this. And that would be locating our first point. So we can see on our table here that we have our first point of 3, -4. Next, we give values to x differing from 3 by equal amounts. So by this, we're going to take 3 and we're going to go by equal amounts up. So they start by going a half number difference. So we say 2.5 and 3.5 because that's a 0.5 difference upwards. From there, they went for 1 difference, 2 and 4, added 2, 1 and 5, and then 3, 0, and 6. So we find that y has the same value for x minus 3.5 as for x equals 2.5, for x equals 4.5 as for x equals 2, etc. So this table then shows that record of the points and their coordinates. So we have 2.5 and 3.5 both equaling -3 and 3/4. So then we have points B and B beta there. Plotting the points A, B, B beta, C, C, B beta, etc., whose coordinates are given in the preceding table, and drawing a smooth curve through them, we obtain the graph of y equals x squared minus 6x plus 5, as shown in the figure here. So when y equals 0, that is, when x squared minus 6x plus 5 is equal to 0, we see that the curve crosses the x-axis twice at the points x equaling 1 and x equaling 5. Therefore, the roots of the equation are 1 and 5. A curve like that obtained by plotting the graph of x squared minus 6x plus 5, or of any quadratic expression of the form ax squared plus bx plus c, is called a parabola. Therefore, all of your graphs for these equations should come out to be a parabola or a U-shape. If they don't come out that way, odds are you've done it wrong, or there's a missing number somewhere in that equation, because all of them should turn out to be like this. Now, what you can do is you can take the chart that we previously looked at, and your graphing calculator should have a way of plugging this information into the calculator, and then spitting out the chart, and from there you can move the little cursor along the lines and find out what the x-axis says, giving us our roots for the problem. However, if you don't, then it's very easy to graph them, we've already gone over graphing, so it's very easy from there to just graph the points onto your own graph and find out what the x-axis shows for yourself. Alright, let's go over example 1 together. So we're going to solve graphically the equation x squared minus 8x plus 14 equals 0. So, as I said, because there's a 1 here, we're going to take half of this, which is 4. So we're going to plug 4 in as our first number. So we're going to say 4 squared minus 8 times 4 plus 14 equals 0. And they've already given it to us, so we already know that this is -2. So our first point we're going to do is come down here and put -2, 4 on the chart. And then we're going to go up by just one digit each time. So we're going to go to 3 and 5, 2 and 6, and 1 and 7. Just increasing both numbers by 1 each time we go up. That helps give it that U shape when we are formulating it, as well as gives us a nice sample size to choose from. You really want your sample size for something like this to be between 4 and 5 numbers. As we've mentioned in previous lessons, you want it to be at least more than 3 because that gives you more of a pattern. However, because we're starting with a 1 base number in order to get the bottom of the parabola, you really want 4 or 5 to really reach it up as far as you can on the charts that are provided for you. So plotting these points and drawing a smooth curve through them, we have the graph of y equals x squared minus 8x plus 14, which crosses the x-axis approximately at 2 6/10 and 5 4/10. Therefore, to the nearest tenth, the roots of x squared minus 8x plus 14 equals 0 are 2 6/10 and 5 4/10. So again, your calculator would help you be able to find that as close as you can. If not, you'd have to sit here and look at it and go, well, it's not exactly midway through. It's closer to the bigger, so this would be 0.6, and this is closer to the smaller, so it would be 0.4. You know, and then obviously, so you'd have to figure it out for yourself. Alright. So like I said, equations, or 2 and 3 are the same in the fact that we're taking x squared minus 8x plus 16 this time, and x squared minus 8x plus 18 this time, equaling to 0. So they're basically the same. They're working through the same methods. They're still using 4 as their base and going up by 3, 5, 2, 6, 1, 7 for both of them. But you'll notice the numbers have changed. So because of these numbers here, that drives our parabola up farther and farther away from the roots line. So for this one, they only have x equals 4. There's only one root for this equation. So you would actually probably say that x equals 4 and x equals 4. You'd probably put it as 2 equations. However, you can just list it as x equals 4 if that's easier for you, as the a sits right on the x line. And for 3, there is no real root, so you would just put no real root, or you could just write the word root with it all crossed out, because there's no point on the parabola that sits on the x-axis, and you really need a number to sit on the x-axis in order to have a root. So in each of the preceding graphs, the point A, whose y distance is the least of any point in the graph, is called the minimum point. So that's what we're doing by selecting 4 as our minimum point, or figuring that out as I previously showed you, is you're finding the point that's going to be at the bottom of the graph that then helps expand outward. So that is what you're doing for your first couple of lessons, actually. Your first couple, you're going to be looking at solving quadratic equations. And so that was your classwork for this first lesson, and then you have for homework, you're going to have 1 through 4. For tomorrow's classwork, you have questions 5, 7, 9, and 11. And for homework for tomorrow, you have 6, 8, 10, and 12. So, I will see you next time.